Okay, welcome to the status of TensorFlow on Arm-based HPC. Now, what we're going to do is not cover the detailed workflow of what TensorFlow is. I'll give you an overview of that, but specifically how we're making progress in running TensorFlow in an Arm-based environment. So we're also looking to encode TensorFlow on AArch64 in such a way that it is optimized for the various ISAs. So whether your silicon is running 8.1 or 8.2 and potentially 8.3 soon for some people, maybe. We want to ensure that each of the commands which are hardware benefiting or benefiting by the new hardware, that they are incorporated into TensorFlow optimizations. But rather than just leave it at the library, we're also going to see how we can use TensorFlow in a real-world application, such as an artificial intelligence solution. So this is the work that is ongoing currently in a group called AI on Servers, and that's a collaboration with our other project members called AI/ML group as part of the overall Linaro's project collaborative approach to artificial intelligence. So currently TensorFlow does compile and run on AArch64 hardware. So problem solved. Okay, we can go. Everything's sorted. Actually, it's not quite right. It does compile if you've got specific versions of libraries. So the underlying dependencies, if they are there. But the moment you start modifying those dependencies, then the specific version of TensorFlow may or may not compile easily. So what do I mean by that? Well, let's just point out what TensorFlow is anyway. I said I wasn't going to go into the absolute details, but it's a method of creating from scratch machine learning models. So you may hear about edge devices using machine learning models, but where do those models come from? Well, they're created in training sessions or model creation sessions using frameworks such as TensorFlow. Others could be PyTorch or DNNL, or maybe they're hand-coded. But the difficulty is that you basically not just need to be a data scientist, you also need to be a software engineer to encode the training of these models. So it's quite complicated. Now, we know Google is trying to address this with Google Cloud functionality. And what they're doing is automating as much as possible the process of selecting data, refining the data, training the data, and optimizing the resultant model. So that's fine when you're using generic models or generic environments, but what happens if you've got a bespoke solution that you need to encode? Well, it's back to hand coding in either Python or C++, calling to the relevant libraries to do so. An extra tool which you may require is if you've got the data coming in to your data set in not an ideal format, then rather than hand coding every single line concatenation or string chop as required, then there's a tool called Keras, and Keras can help to align the data into regular text formats, of which is more easily consumed by TensorFlow. Now, TensorFlow generates models. Now, those models could be several layers deep or include several neuron or nodes within each layer. But how many do you actually pick? Is it randomly selected, such as 5 layers with 6 nodes each? maybe it's 6,000 nodes with 10 layers. To try and figure out what would be the best approach isn't always easily done by hand. And so looking at ways that this could be done, we can follow AutoML principles. And there is an application called Keras Tuner, which is for hyperparameterization tuning. And what that does, it specifically looks into number of layers or number of nodes within each layer that is required within given ranges. That sounds great, but we started out with a title about TensorFlow and HPC. Well, why do we need HPC? Well, if you start to think of the number of possibilities of layers, nodes that could be part of a particular model, plus the size of the data sets that you're likely to be crunching to actually define the model, then you're going to need a high performance computing system to be able to do that training. So the number of iterations when you're tuning grows significantly. So this is why we need TensorFlow and the other frameworks to be available within the HPC environment. Now, we know they are in the x86, but we're in an Arm-based conference, so we'd like them to also be first-class citizens in the AR64 environment. So the particular versions we've been looking at, so the last version of version 1.15 or 15 was released in the middle of last year, and there will not be any further version 1 being released. And as of earlier this month, version 2.2 has been released, and we understand that there is some conversion issues going from version 1 to version 2. Now, as of a few days ago at the TensorFlow Dev Conference, there was an implication of that 2.2 will actually be a little bit more backward compatible to the existing 1.15 libraries. So we need to investigate how more easily it allows you to do the translation between the older versions. And the reason for doing so is at the end of this year, Google will actually stop training jobs on version 1.15. They are, in essence, forcing you over to the version 2, which can be a good thing because moving over to whatever the latest and greatest is can offer benefits. Now we have to highlight that there has been a little bit of reluctance initially moving from version 1 to version 2, simply because of benchmarking. Now, benchmarking, so if you want to sing the praises of the particular system you've got, you want the best performing benchmarking. But apparently in version 1, the benchmarks work better in than version 2. So you can understand the reluctance to not want to do the latest benchmarks highlighting version 2 performance. This is something that we just need to encourage the transition over, and where there are optimization issues, then that's where we need to look into them. Now, I say we want to make ARM64 the sort of first-class citizen for TensorFlow. Because if you actually look in the TensorFlow community builds, then you'll find sort of quite surprising results. So in the official builds, the only time ARM64 is mentioned is as Raspberry Pis. And we started out this conversation by saying, let's put TensorFlow on HPC. Don't quite think a Raspberry Pi is up to the I/O characteristics of high performance computing, but fair's fair. It's a server function, albeit a very small device. So we don't mind it being on there. It's just that we'd also like things like ThunderX2 to be on there, maybe A64FX with SVE on there as well. So rather than just the particular chips, it's the entire system. So over the last couple of weeks, we've had announcements of ThunderX3 and then the Ampere Ultra. So the Ultra being 80 core and the ThunderX3 being 96 core with multi-threading. So these are significant devices, significant silicon that can be put in server chassis and scaled to high performance computing levels. So it makes sense that we try and apply some pressure or talk nicely to Google to say, come on, can we have the official builds, please, for TensorFlow on ARM64. Of course, sometimes we're driven by community rather than just the official builds. But if we look at the community build status, then we see AMD's ROCm GPU, we see the PowerPC GPUs and CPUs, and we see Red Hat Linux at version 7.6 on CPU and GPU in x86. Because it's a little odd. We see Red Hat just at the bottom there, simply because if we just go back, you'll notice that what you're not seeing, it just says generically Linux CPU, Linux GPU. But if you look at any of the recipes on Google searches on how to build TensorFlow, more than likely you're going to find that they're Debian builds. Okay, and quite specifically on the Raspberry Pis, they're Debian builds. What Linaro likes to do is encourage distro agnostics. Whilst, of course, we accept Red Hat is very much a member of Linaro, and it's great news. We want to make sure that what we develop applies to all major distributions as well. So we like to encourage recipes which allow Debian, Red Hat, SUSE scenarios to be listed on these sort of build status. So let's see if through encouragement we can increase the number of items on these build status lists. But we are limited in what versions are required, because TensorFlow requires the build system from Google called Bazel. And Bazel has its own dependencies. And currently, the latest shipping version is release 2.20. However, we are using something like 0.89 as a release level, simply to try to get TensorFlow to build on AR64. So a 0 release, you can imagine that there's going to be some difficulties or some features which are not carried through to the latest solutions. So we'd like to sort of work with the community so that we can fix all the issues between what is preventing Bazel to be loaded. So we ask the community to get in contact with us and assist both in the TensorFlow builds itself and the underlying dependency of Bazel. So the application of what we're looking for TensorFlow. So we have a group called AI on Servers within the HPC group. And so we collaboratively go with the Edge device team that are looking at AI/ML. And we look at more than one framework. So we have TensorFlow and PyTorch, and we're also looking at DNNL and the integration of DNNL with the above frameworks as well. So we're focused on the data center. So I'm director of the LDCG, or Data Center and Cloud Group, and we'd like to see our high-performing ARM64 devices doing the training primarily. They can, of course, do inferencing, but if you're out at the edge and you're unable to carry a 2U chassis around with you, then, of course, you want the edge devices, the smaller devices, to actually do the inferencing. So we look at the reinforcement training to make sure that what is being modeled is effective. And if it's not, then we feed back into a feedback loop, an iterative feedback loop, to tune the models effectively. And we're looking sort of beyond ML as well. So we understand that TensorFlow is primarily a machine learning environment, but ML is a subset of AI. It's not a superset of AI. And so we're looking at the broader range aspect of AI on servers, of which ML and TensorFlow would then be an operational part of it. Now, we have some resources available, and we encourage community assistance as well to optimize TensorFlow and the various libraries for SVE and the upcoming SVE2. Both are supported in the GCC and LLVM compilers already, so you don't actually need hardware to run these particular versions. You can use software emulation models so that we have the software available when the silicon is also available. And the key difference also for AI on servers is the online dynamic approach. So conventional models are trained by throwing a whole load of data at the training environment, and then working on the model. And once the model is done, you take the model and you use it. But if the data structure changes, you have to throw away that model and start with a whole new data set and do a complete retrain to generate a new model. Now, each new model could take hours or days or even weeks if you're talking about billions of layers or billions of data items in which to calculate. And then this is also why we need HPC or exascale computing even for the very large data sets. But really of interest is the online dynamic nature of the potential for AI learning. So you actually report back, or such as say a reward mechanism, if something is identified correctly, versus a negative reward system if something is identified incorrectly. And so that over a period of time, you can tune the intelligence that is being utilized. Now, we don't just look at frameworks, we look at underlying libraries, and we look at OpenCV, OpenCL, and OpenMP. Each of those need further optimization to make use of the SIMD architectures, such as the earlier versions of Neon, and then subsequently SVE and SVE2. So we'd, again, like community support from that, for that. And these are the sort of environments that we're looking for training methods. So this is where we can apply TensorFlow in straightforward image classification. We've heard about the 11 million cats to identify a cat, whereas a child will be shown maybe one cat over a period of time and realize that over a period of time that it's called a cat. So there's a differentiation between massive data sets and learning like a child. So object detection, we see the automotive industry doing some collision avoidance systems where they know they've got models which identify what cars look like, what pedestrians look like, cyclists, etc. But we're looking to see if we can get sort of TensorFlow to move beyond just those basic object detections and look at the further AI a more intuitive way. Because what happens if a new car design is brought out that doesn't look like previous car designs? Well, you have to go back to the drawing board and do a whole new set of data to recreate the model. Yet a human's observation of a new car would think, okay, it's new, but overall, fundamentally, it looks like a car. And so this is the area between pure computation and a bit of intuition or understanding. So at the bottom of the screen, you see perception, understanding, discovering, prediction, creation. These are the approaches as to where we want to really push the underlying libraries. And if we can get them to so not just rely on HPCs, but maybe the HPC is in the cloud and the edge devices are doing the latency sensitive solutions, but then the edge device is referring back to the cloud to receive updates. And in fact, there's a company, I think Neurala, they offer a cloud solution talking to edge devices, which do pretty much that. The edge devices feed back changes to the model is recalculated in the cloud, and then the cloud re-downloads back the updated model. we don't really want to test all these things out in the open environment. It could be a little dangerous having a robot running around a roadway. So we like test environments. So here's a list of 5 different sort of AI environments, the DeepMind Labs, Google Researchers, the Habitat from Facebook, NVIDIA's Isaac SDK, coincidentally, so Paul Isaac, but nothing to do with me, and the Cyberbotics Weebots. So we'll be looking at proving the optimization, first of all, of the TensorFlow library, but then the application of that library, how it performs in these test environments. And so if you're looking to actually test any of your own codes, we can look at hosting some of these potential environments. And we host these things in our co-location facility, currently in London, and some elements of it in the US as well. And we encourage developers who want to try their solutions on ARM hardware, ARM server-based hardware, to get in contact, and then you'll be able to test your solutions on the large HPC environment that are typically run. Now, to give an example of a large HPC, which is ARM, well, Sandia National Labs, they have the Astra solution. And then we have Fugaku running the A64FX, which is currently being constructed in Japan through Fujitsu and Riken. Hopefully we will get access to those as well. So where are we technically? So just as a sort of a wrap up. So we're currently reconfiguring our hardware in the co-location facility. We're looking to have a truly scalable environment. So we can go from a small number of nodes to a large number of nodes, depending on the build scenario that's required, and then scale it back down to be sort of efficient use of the energy, so electricity. And ARM is helping by providing some of the build recipes for TensorFlow and MLPerf, and so we work alongside all our members and their member engineers, so that it's not just Linaro coming up with sort of the software or the build scenarios, that we actually encourage a collaborative environment. And we will obviously recognize where the source of the solution came from. So we are currently reviewing our own TensorFlow continuous integration solution. To be fair, we've got a couple of issues with Python 3 in the build, but that's ongoing. However, you can see our GitHub page if you'd like to contribute. I made reference to a GitHub page on a previous slide also for the AI on servers, in case you've got some examples that you'd like to upload. And what we're currently been doing also is just making sure that OpenCV works on AR64, which is very, very easily done because it even works on the Raspberry Pi. But we'd like to scale it up in optimization. And we still have plenty of things to do. So OpenCL, OpenMP are required. We've got some test platforms for the new Neoverse N1 solutions, which will be the ISA version 8.2, whereas the current shipping hardware is 8.1. So it's a benefit to have those available. And then we do plan to test containerization so that we can improve the scalability of the build scenarios. So with that, if there's any final questions, other than that, please feel free to contact us on aionsservers@linaro.org, or offer to submit on the GitHub page any of the examples. Is there a TensorFlow 2x package or Docker image available now to run on ARM64, and where can I get it from? I personally don't have the Docker images available. I know that NVIDIA has been containerizing elements of it, but it's something that we do want to get into, but we don't have available yet. Thank you very much.